Okay. Okay. So, welcome to the next TA session. Um, this is the fifth TA session for the course Principles of Signals and Systems offered by Professor Aditya Jagannathan from IIT Kanpur. My name is Yashvanth. I'm presently a PMR Ph.D. student at the Department of EC, IISc Bangalore. I work with Professor Chandramurthy, and my research interests lie in signal processing and applications to wireless communication systems. I currently focus on a technology called intelligent reflecting surfaces and how to use them and how to optimize it for the application in wireless communications, next generation wireless communications. So, if you have any queries about the contents that I'm delivering in the TA session, you can feel free to email me in this email that I show that you see above, and you can know more about me, my research interest, and the kind of topics that I work about in this particular web link. So that's basically a very quick introduction about myself. So the topics that are going to be covered for today will be broadly on Z transforms. Okay, so as usual, the first part of the lecture, the TA session today will be on summarizing the week 5's lectures, which is broadly on Z transforms. Okay, so what is Z transform? Z transform is basically, I would say that. Oops, sorry, just a minute. Yeah, Z transforms are basically um, the transforms that are used to represent and analyze discrete time signals and systems. So just like how Laplace transforms we saw in the previous class was used to represent and analyze continuous time signals and systems, exact counterpart or the equivalent transform that is used to analyze discrete time signals in systems is basically called the Z transform. Recall what is a discrete time signal? That if you have x of t as a continuous time signal, you basically here t can be any real number. It's a time index, any real number. But for discrete time signal, it is denoted as x of n, where n takes only some integer points. So only at integer points, I will measure the amplitude or I will measure the signal values. Such type of signals are called discrete time signals, and systems which processes such kind of discrete time signals are called discrete time systems. So in the context of discrete time signals and systems, the analogous transform that is used to simplify our representation and calculations is called the Z transform. So it's a counterpart of Laplace transform. And how is Z transform defined as? X of Z is defined as sum over x of n, z power minus n, and n ranges from minus infinity to plus infinity. So just like how in Laplace transform, the Laplacian variable s was a complex number, here z is the letter you use to denote a z, the Z transform domain, and it's also a complex number. So you can write, and if you recall, that any complex number can be written as r times e power j omega. So the difference is in Laplace transform, we used to write s is equal to sigma plus j omega, like in a plus jb form in the Cartesian form. But for Z transform, we represent the complex number in polar form, where r is the amplitude of the complex number and omega is the angle made by the complex number z on the complex plane. So this is what I'm describing here. So if you plot the real part of z and imaginary part of z on x and y axis, the basically the radius, that is the amplitude, will lie on the r domain, that is like the radius domain, and omega is the angle made by the complex vector, or basically if this is your z point, the angle made by this vector with respect to real axis is called omega. Right? This is basically called the polar domain representation for we use polar domain representation in Z transforms. Okay, so similar to how we have region of convergence in the case of a Laplace transform, we also have region of convergence for a Z transform. That is, what is it? Basically range of Z for which the Z transform converges. That is, this number should be a converging number less than infinity. For all values of Z for which this number is less than infinity is said to constitute the region of convergence. So let's take an example. Let's say x of n is a discrete time signal as a power n u of n. Now you can show that just use this x of n in the above expression, and then you can show that using the properties of series. In particular, it will turn out to be like a geometric series, infinite geometric series. U of n basically takes a value pos 1 for n greater than 0 or and 0 when n is less than 0. So this in summation will now become n is equal to 0 to infinity, because because for u negative number it is 0. So you have z power minus n into a of n. So this is nothing but an infinite geometric series. So basically compute that sum and you can show that x of z turns out to be this number 1 by 1 minus a z inverse. However, that geometric series admits this formula only if a z inverse is and modulus of a z inverse is less than 1 or mod of z is greater than a. Okay, so this basically multiply by z on numerator and denominator, you will get z by z minus a. So basically x of z, the z transform is given by z minus a, with the ROC given by mod of z greater than mod of a. Now what is this essentially saying? What I'm saying is you take the amplitude, that is the radius of the complex number, and that should be greater than mod a. So basically let's say a is some real number, let's say, and mod a is something like this. So this is nothing but the region which is outside, exterior to the circle mod z equal to a, right? So if you recall, for any complex number z, mod z equal to c is a locus of a circle around origin, right? So if I'm saying mod z greater than a, that means all parts, the region are exterior to the circle mod z equal to a. Okay, so the ROC now is the exterior part of this circle, and in this ROC, in this region where the Z transform converges, Z transforms equals Z over Z minus A. Okay, now let's take another example. Let x of n be a power n u n minus n minus 1. That is, recall that u minus n minus 1 is a left-sided signal. Okay, un is a right-sided signal, but u minus n minus 1 is a left-sided signal. Again, just use the expression above. Basically, for you use this value of x of n and put it over z transform expression. Whatever answer you get will turn out to be this number, z by z minus a. You just look, z by z minus a was for a to the n, a power n u of n. It is also becoming the z transform for a power n u of minus n minus 1. These are two different signals, but they're having the same z transform. Then where is the difference? The difference is in the ROC. Just like how in Laplace transform we saw that two different time domain signals can have the same Laplace transform, but their ROCs will differ. Similarly, even for discrete time signals, you can have two different discrete time signals mapping to the same Z transform, but their ROCs can be very different. In fact, here it is mod Z less than mod A. That is, it is interior part of the circle mod Z equal to A. But for the previous signal, it is mod Z greater than mod A. That is, it is the exterior part of the uh, circle mod z equal to a. So what this means is that different time domain signals can have same z transform expressions. Then what is the difference? The ROCs. So in order to be uniquely or fully characterize a discrete time signal, one has to mention the region of convergence also. Okay, without mentioning the region of convergence, your z transform x value or the for whatever you z transform you report is not valid. It's incomplete. It's incomplete way to represent Z transform. You should write the expression, also mention in which region does this expression hold true. Okay, so now let's again, now just like how in Laplace transform we saw some properties, similarly for Z transforms also you have so many properties which are very similar to Laplace transform, and we'll just quickly go over that. I have taken this table. This is table 10.1, and the reference is Oppenheim Signals and Systems, chapter number 10. Okay, you take the table 10.1 in chapter number 10 of Oppenheim. That is what is this table. I've just copy pasted, taken a small picture, and I've pasted it here. Okay, so okay, let's just understand. Let x of n be one signal whose z transform is x of z. Let x1 of n be another discrete time signal with z transform x1 of z, and x2 of n be another discrete time signal with z transform x2 of z. And let the corresponding ROC, region of convergences, be R, R1, R2. Okay, now the first property goes by the name linearity. So what it says is that if x1 of n is a z transform of x1 of z, and x2 of n is a z transform of x2 of z, then ax1 of n plus bx2 of n will have the z transform ax1 of z plus bx2 of z. Okay, and what about the ROC? ROC will be at least intersection of R1 and R2, which is the ROCs of individual signals x1 and x2. Next property, this is the same as Laplace, right? Laplace also we had the same property. In fact, we will see that we will study more transforms in this course, like Fourier transforms and all. There also you will see that linearity will hold everywhere. Okay, the fundamentally this is because most of the transforms that we will be encountering in this course, in fact, all transforms are all linear transforms. That's why they automatically satisfy what is called a linearity property. There are non-linear transforms are not, they are much beyond the scope of this course. So generally all transforms that we will be looking in this course will typically satisfy linearity property. The next property is called the time shifting property. So what does time shifting property say? That if you have a signal x of n whose z transform is x of z, then the signal x of n minus n naught, that is you delay by a factor of n naught, will have the z transform z power minus n naught into x of z. You recall for Laplace transform, what was the scenario? We had x of t minus t naught became e power minus st naught into x of s, right? It is very similar here also. Instead, that e power minus s is now taking the value of the z variable itself, z power minus n naught. So it's like e power minus s you replace by z, and what t naught, it becomes n naught. That's the only difference. So it looks very similar expression only, right? So this is the time shifting property of the z transform. Now scaling in the z domain. So what happens is, if you have a signal x, of n whose z transform is x of z, then you can show that e power j omega naught n times x of n will have the z transform x of e power minus j omega naught z. Or if you let's say write z naught power n times x of n, its Laplace z transform will be x of z given z naught. Similarly, if you have a power n x of n, its Laplace z transform will be x of a inverse z. Okay. These are different ways of basically showing that you have scaling in z domain. For example, here is z is scaled by e power minus j omega naught. In the second case, z is scaled by 1 by z naught. In the third case, z is scaled by a inverse. So these are different ways of scaling a z transform. So these are all properties under the scaling in the z domain property. The next property goes as follows. If x of n is a time domain signal for which the z transform is a capital X of z, then x of minus n will have the z transform x of z inverse. Okay, and the ROC will be inverted z. That is, if R is the ROC of x of n, then R inverse will be the set of all points z inverse where z is in ROC R. Okay, that is basically the ROC of x, the z transform of x of minus n. Now time expansion, maybe for now you ignore this. This is basically something that is little advanced. So there is in at least these are called discrete time signals, right? So basically these are the properties of discrete time signals. So there is a follow-up course called digital signal processing or discrete time signal processing. Both are synonymously called. And basically what you can show is that there is a property called interpolation and decimation. Okay, it's a property that is unique to a discrete time signal, and this is like that. Okay, basically what it says is I will do decimation. I will ignore some numbers in between. I will only subsample the given discrete time signal. That is basically called time expansion. But maybe this is not something you can ignore for now. Maybe after doing a course on digital signal processing, you will be able to understand time expansion property better. What is this operation? What is this operation exactly doing? You can learn it later. Conjugation. So what conjugation says is, if x of n is a time domain signal whose z transform is capital X of z, the next conjugate of n will have the z transform x conjugate of z conjugate. In fact, we will use this property in one of the problems for today. Okay. Next is the convolution property. What it says is that if I have two signals x1 of n and x2 of n whose z transforms are x1 of z and x2 of z, then the convolution, the z transform of x1 of n convolved with x2 of n will be x1 of z times x2 of z. So it's a convolution in the time domain is the product in the z domain. So in Laplace transform, we also had the same relation. x1 of t convolution x2 of t will have the Laplace transform x1 of s into x2 of s. This is same as that only, except that this is for a discrete time signal, and you have the z transform instead of Laplace transform. But the structure is the formula remains the same. Now, first the difference. What is first the difference mean? It is x of n minus x of n minus 1. Now, you should remember that it's a discrete time signal, right? So, the whatever you had in continuous time called derivative of x of t, this in the discrete counterpart, you cannot take differentiation, right? Because it's no more continuous in t. It's a discrete time t. So, this d by dt of x of t becomes x of n minus x of n minus 1. That is, you just take the difference between two consecutive samples. That is the difference. This difference is like the differential in the continuous counterpart. Okay, so basically this first the difference property is like the differentiation property of your z Laplace transform. Okay, and what this property in z transform says is that if you have x of n as a whose z transform is x of z, then x of n minus x of n minus 1 will have the z transform 1 minus z inverse x of z. Okay. Accumulation means you sum over x of k. This counterpart is an integration. If you remember, in continuous domain you have minus infinity to t x of tau d tau. This is like an integration in continuous time domain, but this is for a continuously varying x of tau. That is for a continuous time signal. But for a discrete time signal, the counterpart of integration is nothing but a summation. Okay, this accumulation is like the integration we had seen the Laplace transform property. So the accumulation property says that sum over x of k from k equal to minus infinity up until a number time n, the Laplace z transform is 1 over 1 minus z inverse x of z. Finally, differentiation in the z domain. Note that only in the discrete time domain you cannot differentiate because n is a only integer value. It is not continuous. But z is a continuously varying complex domain. So you can differentiate z transform in the z domain, but you cannot differentiate time domain signal in the discrete time domain because n is a discrete valued sample. So you can have something like a differentiation in xz domain. What this says is that if x of n is a z transform, has a z transform a capital X of z, then n into x of n will have the z transform minus z times d by dz of x of z. Okay, so basically these are the different properties of z transform. Very similar if you basically now take your Laplace transform, keep the table side by side, and you can observe most of them, the similarities. They're very similar. Okay, and finally there's something called initial value theorem. Again, if you recall, in Laplace transform also we had something called initial and final value theorem. For now, I am not going to discuss that, but this is what is the initial value theorem. Basically, initial value theorem is used to find the steady state output of any system. Okay, discrete time system, at least in using z transform. But we will now not worry about this. Later in the course, we will talk about this in detail. Okay, so are there any doubts? Okay, let's move on then. Now some examples. Okay, like how we saw that e power minus at into u of t had something like 1 by s plus a, right? Something like this, or s minus a, whatever. We had something like this as a Laplace transform. Similarly, what are some very common z transform pairs like Laplace transform? Similar to Laplace transform, a delta of n will have the z transform equal to 1, and the ROC is the entire z plane. Unit step function u of n will have the z transform 1 over 1 minus z inverse, and the ROC is mod z greater than 1. That is, what does it mean? You take the unit circle at mod z equal to 1, and the exterior part of this is nothing but your z transform of u of n. And now you take the other side, minus u of minus n minus 1. That will also have the same ROC same z transform 1 over 1 minus z inverse, but the ROC is exactly the opposite. That is it is mod z less than 1. That is, you take unit circle of radius 1, and if all the region inside the unit circle is the ROC for this signal minus u of minus n minus 1. Delta of n minus m. The Laplace, the z transform is z power minus m, and ROC is all z except 0. For example, how did I get this? So we basically time shift this first signal by unit of m. Go and see the property. What is the property? X of n minus n naught will have the z transform z power minus n naught x of z. Now, what is x of, sorry. Now, what is x of z? X of z is nothing. Here, x of n is like delta of n. Okay. For delta of n, what is the Laplace transform is 1. So, x of z is basically equal to 1. Right. So, what multiplies x of z is z power minus n naught. Here, n naught is what? N naught is equal to m. That's why it is z power minus m into 1, which is equal to z power minus m. That's why the transform of delta of n minus m is equal to z power minus m. You can just derive this from 1 and the properties of z transform. Now, going back to some more important signals, alpha power n into u of n. The z transform is 1 over 1 minus alpha z inverse with ROC mod z greater than mod alpha. That is the exterior part of the unit circle, which is equal to mod z equal to mod alpha. You take the exterior part of this circle, that is the ROC for this alpha power n u of n, and its z transform. Similarly, minus alpha power n into u of minus n minus 1 will have the z transform 1 over 1 minus alpha z inverse with ROC mod z less than mod alpha. Similarly, n times alpha power n into u of n will have the Laplace z transform alpha z inverse divided by 1 minus alpha z inverse whole square with the ROC z mod z greater than mod alpha. Now, you see what difference between 5 and 7. Right? Only you multiply by n on both. N to n, you multiply n to equal signal in 5, you get signal 7. Now you go back to the properties. What it says is if x of n has a z transform capital X of z, then n into x of n will have the z transform minus z into d by dz of x of z. Now use here x of z, you use this number here. So basically what you do d by dz of this and do minus z outside. Whatever is this value you can verify that is equal to this number here. Okay, that's how you need to use the properties of the z transform, and you should know, it's better to know the transforms of some basic signal and then use the properties and derive the transform for other higher order or other complicated signals. Similarly, you take the signal in number item number 6. So that is basically, if you look at 8, it's nothing but only thing is you have multiplied n to equation, the signal in 6. So what you do, you take this number, you differentiate with respect to z and multiply with minus z. Whatever is the answer you get, that will be this z transform here. Similarly, you can show that cos omega naught n times u of n will have this as a z transform with ROC this. Sin omega naught n into u of n will have this as a transform. R power n into cos omega naught n into u of n will have this as a transform. R power n sin omega naught n into u of n will have this as a z transform with ROC mod z greater than mod z greater than R. Okay, fine. So now we have basically what we have seen is z transform, and we have seen some properties of z transform, and we have seen some examples. Now, okay, now what did we do? We took a time domain signal and we used z transform, and we analyzed the signal in the z domain. Okay, now from given z transform, how do I come back to time domain? That is called inverse z transform. The expression for that is x of z is equal to summation n equal to minus infinity to plus infinity x of n z power, I think it's plus n. So if you go back to the definition of z transform, it has z power minus n. So for inverse z transform, it should be plus n. Okay, it should be z power plus n. Now, what are some typical ways to compute inverse z transform? One easy way is what is called power series expansion. So the idea here is that you given some z transform, express the z transform as a power series in z. Then the coefficient of z power minus n or z power plus n is x of n. Okay. Now another second trick is called partial fraction. In partial fraction, what you do is that you express your given Z transform as numerator divided by denominator function of Z, and that is basically given by something like this. Now here Z, the zeros of your numerator is called the zeros of the Z transform, and the zeros of your denominator is called the poles of your Z transform. Okay. Now if your poles are all simple poles, okay, then what you do, you express x of z divided by z as something like this, as partial fractions. Okay, that is each pole you express as one partial fraction, one fraction with appropriately scaled coefficients c1, c0, c1, and so on to cn, where p1 till pn are the simple poles. Then you can show that the c0, c1, and so on to cn will admit this, will have, and where this is a c0 to ck. Then what you do, you invert each of these terms using the properties of Z transform. You invert each of these terms, and the sum of all the inverse Z transform is the actual inverse of the full Z transform x of Z. Now, if you have poles with multiplicity, let's say your pole pi is repeating r times, then corresponding to that pole, you should express, there are r terms. You should express r terms. Like how if you had simple pole, only one term is enough for one pole. You should have r terms where each term will have a different odd degree of the, or different exponent of that particular z power minus pi. And how do you find the value for lambda 1, lambda 2, and so on to lambda r? Similar to how we did for Laplace, inverse Laplace transform. Where basically you can show that lambda r minus k equal to 1 by k factorial d power k by dzk of z minus pi whole power k into x of z by z at z equal to pi. Okay, so these tricks we will use. Today we'll see how to use them and invert the z transform. Now, properties of region of convergence for a Z transform. Like as Laplace transform, the ROC does not contain any pole. Okay, like a Laplace transform, for Z transform also, for any finite sequences, ROC is entire Z plane. You remember in Laplace transform, we told that finite duration signals in the time domain will have full S domain as a ROC. The counterpart, this is a counterpart in discrete time. That is, for a finite sequence, the entire Z plane is the ROC. For a right-sided signal, ROC takes the form mod Z greater than R max. What is R max? R max is the largest magnitude of poles of x of z. Recall in Laplace transform, what did we say? Right-sided signal will have a right-sided ROC. That's what we told for Laplace transform. Here, instead of saying right-sided ROC, we are saying it is the exterior part of the circle with radius equal to the largest pole. Here in Laplace transform, we told that the number from which ROC starts, this represents the large magnitude of largest pole. But for Z transform, the circle with radius will represent the magnitude of largest pole. Okay, so exterior part of the circle with largest pole will be the structure of ROC if the discrete time signal you're considering is a right-sided signal. Similarly, if it's a left-sided signal, the ROC will be interior part of a unit circle with radius given by the R min, which is the smallest magnitude of poles of the Laplace Z transform x of z. Okay, similar, this is like a Laplace transform. Laplace transform, what did we say? If it's a left-sided signal, right? Then if you look at the Laplace transform, we say the ROC should also be left-sided. Here, instead of saying left-sided, we are saying that it is inside the unit circle. You're inside the circle with radius equal to the minimum magnitude pole. And finally, if the signal is a two-sided signal, then ROC is an annular region. Annular region of width, annular region of width R1 and R2, where an R1 and R2 are appropriate poles of your Z transform. This is similar to your Laplace transform. What did we say? For two-sided signal, the Laplace transform is a strip. It's a strip, right? It's a finite strip. Now, this strip has become an annular region in Z transform. Okay, so that's about the properties. Now coming to system function of LTI and LSI systems. Okay, so for an LTI, if the system is LTI and the discrete time, it can also be called as LSI system, that is linear shift invariant system. So what it says is, suppose if you have a discrete time system whose LSI discrete time systems whose impulse response is h of n, and the input is x of n, and the output is y of n, then you can take the Z transform of all these three sequences separately, call it X of Z, H of Z, and Y of Z. Then H of Z, basically, which is a Z transform of your impulse response, is called the system function or the transfer function of your system. How is it computed? You take the output Z transform divided by input Z transform, and that is basically your H of Z. How did I do this? By convolution property. Why? Because what I know is that y of n, for if it's LT system, y of n is given by x of n convolution h of n. But by convolution property of Z transform, your y of z is equal to x of z into h of z, or h of z equal to y of z by x of z, and that's what is written here. Okay. Now, in terms of understanding the characteristics of system, if a system is causal, then h of n should be right-sided. You recall this from the first class. But now we saw that for a right-sided signal, ROC takes a form mod z greater than R max. That is, it should be an exterior part of a circle with radius equal to R max. So if it's an exterior part of the circle, then that system can potentially be a causal system. Now, for stability, what it says is the condition on the impulse response is it should be absolutely integrable or summable because it's a summation. This means what you can show is that unit circle must be included in the region of convergence. So remember, for Laplace transform, using Laplace transform, what we told is if your j omega axis is contained in the ROC, then that continuous time system is a stable system. The counterpart to that is if your unit circle, that is mod z equal to 1, if this unit circle is included in the ROC, then that discrete time system is going to be a stable system. Okay, now determining the output of system using Z transform. Okay, so let's say X of n is the input, Y of n is the output, and H of n is the impulse response. Then what you can show is any linear shift invariant system can be represented by what is called a linear constant coefficient difference equation. So this is similar to continuous time in the sense that there we told that any LT system can be represented as linear constant coefficient differential equation, but for a discrete time system it's a difference equation, right? So that is, we had d power k by dt power k of y of t, but here that is replaced by y of n minus k. That is, you have difference by k instead of taking the kth order differential. Okay, that is for a, uh, a discrete time system. Okay. Now, if you take the Z transform on both sides, basically this is how take the Z transform on both sides of this equation and rearrange. You will get this number. So this is basically the expression for the transfer function of any discrete time system. Okay. Now maybe this is where we were, and I think this is basically the summary of what has been covered till this week. If there are any questions, this is the right time to ask. Okay, I don't see any question. Then let's move forward. Okay, so today I'm going to slightly consider a different approach. Just wanted to do on a trial basis. What I have done is that I have already pre-written my notes for today. So I have basically wrote down the question. I also solved and written in the notes here. So my approach for today is to go through whatever I've written and explain the solution, so that what I've observed in the past is that we were not able to do more questions. I had planned for more questions, but eventually we don't cover end up doing all the questions. So today I thought I will try by I have pre-written the question and answers. We will solve all. We will go through them together, and then we will see if we are able to finish. At the end of the class, you can give me your feedback. Which one you prefer? Do you like me to write in live and show you, or do you prefer this approach where I have already solved it but I want to show you how I solved it? Okay, in the end of the class you can give me a feedback. Okay, so this was just about how to find ROC. I found that in several um, places people had some difficulties in finding how was the ROC in Z transform computed. So I just wanted to show you for as an example. So let's say you consider a signal a power n u of n. Okay. And if I want to find the ROC for its Z transform. Now, what is the definition of Z transform? X of Z is equal to n equal to minus infinity to plus infinity, x of n, Z power minus. Now, put x of n is equal to a power n into u of n. That is this step here. But now what do I know? I know that u of n takes a value 1 for n positive and u of n takes a value 0 for n negative. So for all from minus infinity to 0, there will be no such term. It will be 0. But from n equal to 0 to infinity, you will have u of n equal to 1. So this becomes a power n into z power minus n. Or you can write this as a z power minus 1 whole power n. Now this is like sum over n is equal to 0 to infinity b power n, where b is equal to a z inverse. Now this is nothing but an infinite geometric series which has expression 1 over 1 minus a z inverse, provided this common ratio a z inverse is a number whose magnitude is less than 1. Or if you solve for this, you get mod z is greater than a. So this is how you compute the Z transform along with ROC. Okay, fine. Now let's move to the first question. So the signal given to us is x of n, which is of the form a power n into u of n. Okay. Now the question is find the Z transform of n times x of n. Okay. Now what did from the first itself we saw that the Z transform of if x of n has Z transform x of z. Maybe I can just these small things I can write. If x of n had Z transform capital X of Z, then what we saw from property is that n times x of n will have Z transform minus Z into d by dz of x of Z. Okay, so basically what it means, you just take the you find the Z transform of x of n and you do d by dz of that and multiply with minus Z. Okay, so first we will find the Z transform of a power n into u of n, which is what we did here. This example is also same thing. Okay, so let's just quickly go through. So basically, x of z is nothing but summation minus infinity to plus infinity a power n u of n into z power minus n. That is same as this number, and that basically is giving rise to this. Right now, multiplied by z on numerator and denominator. What you get is that z by z minus a with ROC mod z greater than a. That's what I wrote here. Z by z minus a with ROC mod z greater than mod a. So then what should I do? I need to apply this. I need to differentiate this with respect to z and multiply by minus z. And that's what I'm doing. So n into a power n u of n will have z transform minus z into d by dz of z by z minus a. Right? So then apply the u by v rule. So z minus a first and then differentiate z with respect to z, that is 1, minus z times differentiate z minus a with respect to z, which is 1, and divided by the denominator square, z minus a the whole square, and there's a minus z outside, and that's what here. And this is nothing but minus z times z minus a minus z by z minus a square, or z and z cancel, and this becomes a z by z minus a the whole square with the same ROC mod z greater than a. Okay, that's all. Okay, is this clear? Can anyone confirm if everything until now is okay? You can unmute and just confirm. Hello? Can anyone confirm if everything is clear till now?
Yes, sir.
Okay, thank you. Okay, let's move to the next question. So the question goes as follows. Show that if x of n is a real signal, that is means what? The signal x of n, let's say x of 2, x of 3, or x of minus 2, for any value of n, that output x of n is a real number. Okay. And the question is, if that is the case, then the zeros of its z transform x of z occur in conjugate pairs. That is what I'm saying is that if z is the zero, z naught is a zero of x of z, then z naught conjugate will also be its zero. That is the question that we are going to prove. Okay. So first of all, understand, we'll write what is it mean by zeros of x of z. Okay. So what it says, set of all z points for which x of z is equal to 0. Right. Numerator You remember what did we do? We express x of z as numerator function by denominator function, and we told x set of all z for which numerator goes to 0 or x of z itself goes to 0 is called the zeros of x of z. Okay, so that is basically called zeros of x of z. Okay, now what we need to show, we need to show that if x of z is equal to 0, then x of z conjugate is also equal to 0. That is the meaning of saying that the zeros occur in conjugate pairs. That is, if x is a 0, then x conjugate is also a 0. How to do this? We'll see it. So first, as usual, write on the definition of z transform. X of z equal to minus infinity to plus infinity, x of n, z power minus n. Okay, now what we'll do, we'll take conjugation on both sides. Okay, that's so you take x conjugate will come. So I mean, I'm just taking whole conjugate on both sides. So sum over, so basically the conjugate will now go inside summation and becomes x conjugate of n into, so z is a complex number, remember that. So if you have x z power minus n conjugate, which is same as z conjugate whole power minus n. That's what is this number here. But x of n, what the question says that x of n is a real signal. So x conjugate of n is same as x of n. And this is same as, and this will same x conjugate of minus n. Now what is this? This is nothing but x of z conjugate. Okay, basically because if you see instead of z you have z conjugate, so it is nothing but the x of z conjugate. So what we have first, what we have seen is that we have seen x conjugate of z is same as x of z conjugate. That is, you compute the value of the Laplace z transform at x and then you do whole conjugation. That is same as first conjugating the z and then computing its value at x of z conjugate. Both will yield the same value if x of n is a real signal. Okay, and now what we need to prove, if z naught is a 0 of x of z, then z naught is a 0 of x conjugate of z. That is what we need to prove. I mean, sorry, that is not we need to prove. We can see that. Why? Because okay, if if z naught is a 0 of x of z, what does it mean? It means that x of z naught equal to 0. That is the meaning of z naught being a 0 of x of z. Now do conjugation on both sides. So what it becomes? It becomes x conjugate of z naught equal to 0. But we know that for given signal is a real signal, so x conjugate of z is same as x of z conjugate. So what you do, you basically you can push this conjugation inside z naught. So it becomes x of z conjugate z naught conjugate equal to 0, or z naught conjugate is also 0 of x of z. So we started out by saying that z naught is 0 of x of z, and we proved that z naught conjugate is also 0 of x of z. So what we have seen is that if x of n is a real signal, then the zeros of its z transform occur in conjugate pairs. Is this clear? Is the solution clear? Yes. Hello.
Yes, sir.
Okay, fine. So I think the procedure is clear. But if you don't follow, you should ask me. Okay, unmute and just say which step you don't understand. I will again repeat. You can also ask me something that I've already discussed before. You can ask me to go back whatever I discussed 10 minutes before, 20 minutes before, or any time before. I'm ready to go there and I can again explain if you have not followed something. And by the way, don't worry if you're not able to take notes of this. Anyways, all of them, I think NPTEL, I'm sharing with NPTEL. Are you guys able to access these notes? Can anyone tell me? And I think
Yes, sir.
recording is also, yeah, recording is also now put up on YouTube. I think you also have access to those YouTube links. So both notes and the recordings are available. So the notes you can always take it from from the folder. So you can, it's enough for at least for this lecture. Just concentrate on whatever I'm explaining. Later you can go back to the notes folder and you can just go through them again. Okay. Fine. Now the next question is as follows. If x of n has a z transform x of z, then find the z transform of x of n naught minus n for some integer n naught. Now this is different from what is given in the property. In the property we saw x of n minus n naught. But this is x of n naught minus n. That is, you have reversed your time and also you have shifted your time by n naught. It's not just shifting; it is reversal and shifting. Both are there. Okay, so let's try to again just go by the property. Just use the definition and try to manipulate and manipulate the definition. So we know that for x of n being a discrete time signal, its z transform is given as x of z equal to summation n equal to minus infinity to plus infinity x of n z power minus n. Right, now basically what we can do is as follows. What you do now, let's try to compute the the z transform of x of n naught minus n. Okay, so just have the what is the z transform of x of n naught minus n. Why? Because I've just substituted that. Take multiply by z power minus n and take the summation from n equal to minus infinity to plus infinity. Now what I will do is that I will substitute for variable m equal to n naught minus n. Okay, so then what happens? You see, let's do it again. So that if m equal to n naught minus n, then n becomes what? N is equal to n naught minus n. Fine. So if n is equal to infinity, okay, maybe let's do like, you don't need to do that much. Okay, that is also fine. So you also know that n is equal to n naught minus n. And so that's why what I did, this n I replaced by n naught minus n because of this relation. I have substituted m equal to n naught minus n or n is equal to n naught minus n. This n becomes n naught minus m. Now, if n is minus infinity, what is m? N naught minus of minus infinity, it becomes plus infinity. So, but anyways, it doesn't matter whether you add minus 1, minus 2 or minus 2, minus 1. Addition is symmetric. So I can write this as minus infinity as even, I mean minus infinity even at the bottom. Similarly, if n is equal to infinity, your m will become minus infinity. Okay, so that way also you can write the that, so that way it becomes minus infinity. But again, see, due to symmetric nature of addition, you can bring minus infinity down. Now n naught minus n is m. Okay, is this step clear? How I brought how I changed index from n to m? Is this step clear? Hmm? Yes. Okay, I hope it's clear. Let me know if it's not clear. Okay, now what I'm doing summation over m, right? M. So that means z power minus n naught is a constant as far as this summation is concerned. So you can bring z power minus n naught outside the summation. Z power minus n naught into sum over m equal to minus infinity to plus infinity x of m into z power m, because minus of minus becomes z plus, so it's z power m. Okay, now what I will do, I can write this z power m as z power minus 1 power minus m, so that minus 1 into minus m equal to m. Okay, so that is what I'm doing in the next step. I'm writing z power minus n naught outside, summation over m x of m into x z power minus 1 power minus m. Now what I will do, I will consider the z power minus 1 as some z set in z dash. Okay, then what it means? It means, what is this? Then I'm just writing the inner summation. Nothing but summation m equal to minus infinity to plus infinity x of m into z dash of minus m, which is exactly equal to x of z dash, right? This is the definition of z transform. But what is z dash? Z dash is nothing but z power minus 1. So it is nothing but z power minus n naught into x of z inverse. Okay, so that's what I'm writing. So if x of n has a z transform capital X of z, then x of n naught minus n will have the z transform z power minus n naught into x of z inverse. Okay, is this clear? See what happened actually, very simple. Let's go back to the properties of z transform. What we see? What did we see here? If x of n has z transform x of z, then x of n minus n naught, that is, see, n naught comes later, n comes first, will have the z transform z power minus n naught into x of z. But I have, after this, I have also reversed the sign, right? I have reversed n minus n naught became n naught minus n. So I have reversed it. So I am applying also time reversal. That makes x of z becomes x of z inverse. That's why you have both z power n minus n naught into x of z inverse. Both come into the same place. That is the intuition why you have z power minus n naught into x of z inverse. Is this clear?
Yes, sir.
Yeah. Okay. Now, okay, so this is okay. There's a small question. We will do one thing. We will basically do this question and then we'll take a break for about 15 minutes. Okay. So the question is find the ROC of the Z transform of x of n given by 5 power minus n plus 1 times u of n plus 1 minus 4 power n into u of minus n minus 1. Okay. So let's see. So 5 power minus n plus 1 is nothing but 5 by 5 power n. So this is nothing but 5 into 1 by 5 power n into u of n plus 1. Okay. Now, this is of the form what? A power n into u of n plus 1, of course. But it's, of course, so by shifting by 1, this is nothing but basically what you can do is that you can think of having a power n into u of n. You have shifted to a power n into u of n plus 1. But nonetheless, remember that your ROC depends only on a. The one will only cause a shift in Z domain. The ROC will depend on A only. And in particular, this is a right-sided signal because this U of n plus 1 starts from n equal to 1 and so on, it will be 1, and n less than 1 it will be 0. So it's a right-sided signal. And what is A? A is nothing but 1 by 5. So that's why I directly wrote the ROC as mod Z greater than 1 by 5. And why it's greater than? That's because it's a right-sided signal, so it should be exterior part of some circle. Here the circle is at radius equal to mod A. Here A is 1 by 5 or mod 1 by 5 is also 1 by 5. That's why I wrote the ROC is mod Z greater than 1 by 5. Okay. That is the ROC for the first term. The second term is nothing but 4 power n into u of minus n minus 1. Right? Now, basically, this is a left-sided signal. And what is A is nothing but 4. So, and since it's a left-sided signal, I can directly write the ROC to be mod Z less than 4. Okay. Now, what to do? Now, apply linearity property. The Z transform of basically your x of n is nothing but Z transform of the first term minus Z transform of second term. That is fine. That is not what we are actually interested. We are only interested what is the ROC. Now go back to the properties of your ROC. What does it say? The property says that the ROC is given by the intersection of R1 and R2. That is what is the common region between Z greater than 1 by 5 and Z less than 1 by 4. That is nothing, just draw it and see. Nothing very difficult. Okay, so Z greater than 1 by 5. So mark a radius of 1 by 5. This is like 1 by 5. And anything outside that 1 by 5 is the ROC for the first. This is basically R1. Now for the second one is mod Z less than 4. So draw the ROC for mod Z equal to 4. This is basically mod Z equal to 4. That's the circle for the second ROC, sorry, second term. But the inner circle was mod Z equal to 1 by 5. For the second circle is mod Z equal to 4 and the ROC is interior part. What is the common intersection? The common intersection is this annular region. Okay, between Z equal to 1 by 5 and Z equal to 4. That's what I wrote here. So ROC of x of Z equal to mod Z lying between 1 by 5 and 4. So that means only in this region, the Z transform will converge to whatever we say, right? That 1 by 1 minus A times Z inverse, all those things. Okay, fine. And in fact, this is not very surprising. Why? because as a whole x of n is both to right sided and left sided. That is, it's a two-sided signal. The first term will give you non-zero values for positive n, and the second signal will give you non-zero values for negative n. So as in total, x of n contains non-zero value both for positive and negative values, or x of n is a two-sided signal. But you see here in the today's summary, what did we see? Let me go. Where is that? Yeah, we saw that for a two-sided signal, the ROC is an annular region. That's between R1 and R2, where R1 and R2 are two poles. Okay, here they are basically A's are the poles, right? In this question. So that's why this also admits the same form. That is, ROC is an annular region between two poles 1 by 5 and 4. Okay, so we'll take a break. Is there any question till now? Any question? Okay. If not, let's take break for some time. Maybe we'll meet back again at 7:15 p.m. Maybe just 15 minutes break from now. 7:15 we'll again meet. You all can stay online. Just that you can take some little rest. You don't need to leave the call. Just be on call only, but you can take some rest. We'll meet at 7:15. Okay. Am I audible? Hello? Am I audible? Can anyone confirm if you am I audible? Okay. Yes. Let's continue. The next question says that we need to find the Z transform X of Z. Well, we need to find Z transform X of Z and sketch the pole zero plot with ROC for the following signals. X of n equal to half power n u of n plus 1 by 3 power n u of n. X of n equal to 1 by 3 power n u of n plus 1 by 2 power n u of minus n minus 1. X of n equal to half power n u of n plus 1 by 3 power n u of minus n minus 1. Okay, so let's start with the first one. What and all should we do? We need to find Z transform, sketch the pole zero plot, and ROC. These are the three things we need to do for each of these signals. The first signal is X of n equal to half power n u of n plus 1 by 3 power n u of n. So half power n u of n has a Z transform Z by Z minus half with ROC is mod Z greater than half. That's because it's a right-sided signal, so ROC is the exterior part of the circle at with A equal to half. So that means you basically, if you read the imaginary part of Z, there's a real part of Z, and the y-axis imaginary part of Z. You draw a circle at Z equal to half, and outside the circle is basically the ROC for the first term. Second term is 1 by 3 power n u of n, and which has a Z transform Z by Z minus 1 by 3 with ROC mod Z greater than 1 by 3. That is also similar to the first one. So therefore, now what is the common ROC? Common ROC, if mod Z is greater than 1 by 3, mod Z is greater than half, whichever is dominating, the intersection of these both is nothing but mod Z greater than half. Right? If mod Z is greater than half, obviously mod Z is also greater than 1 by 3 because Z equal to 1 by 3 circle lies inside the circle Z equal to half. Right? So if this is like the intersection is Z greater than half. Therefore, the total Z transform is Z over Z minus half plus Z over Z minus 1 by 3. That is basically this. You just take LCM of the denominators and simplify. You will get this number here with ROC common intersection Z greater than half. Okay, that's because this is what, yeah, this on pole zero plot you need to plot, right? So basically this is your Z equal to 1 by 3, and you say that it should be exterior part of this circle, and Z equal to half is this, and there's the exterior part of this circle. The intersection is that the intersection of Z greater than half and Z greater than 1 by 3 is Z greater than half. Okay, and so what are the zeros? Zero is nothing but, so you equal numerator to 0, so you have Z equal to 0 is 1 0, and Z equal to 5 by 12 is another 0. And what are the poles? Z equal to half and Z equal to 1 by 3. So if I were to draw the pole zero plot, it looks something like this. Real part of Z in the x-axis, imaginary part of Z on the y-axis. Z equal to half, you make a circle, and outside the circle is the ROC. And basically zeros are at 0 and 5 by 12, which are marking by a oval or a circle, and a circle with a cross denotes a pole that occurs at Z equal to half and Z equal to 1 by 3. So we have found ROC, the pole zero plot, and the Z transform. Now the second question is for the signal 1 by 3 power n u of n plus 1 by 2 power n u of n minus n minus 1. It is the same as previous question, except that for the half power n part, u of n became u of minus n minus 1. That is, it became left-sided. In the previous question, both were right-sided. And so if sum of two right-sided will again be a right-sided signal. That's why your ROC turned out to be, the overall ROC turned out to be exterior part of circle. But now here, just by looking at the question, you should be able to guess the ROC. The first term is a right-sided signal. The second term is a left-sided signal. So the sum of a right and left-sided signal is a total signal. That is, it's both a two-sided signal. For a two-sided signal, the ROC should be annular region. So let's see whether that comes or not. Okay. 1 by 3 power n u of n has a Z transform Z over Z minus 1 by 3 with mod Z greater than 1 by 3 as a ROC. That's because the right-sided signal, so it's an exterior part of the unit circle, mod Z equal to 1 by 3. And now the right second signal is half power n u of n minus n minus 1 has, you can show that z transform comes out to be minus z over z minus half. And this will have the ROC mod z less than half. And so basically, what is your total Laplace z transform? Sum of both of them by a linearity property. So you do 2 by z over minus 1 by 3 minus z over z minus 1 by 2, which comes out to be this number here. And now what we need to do, intersection of mod z greater than 1 by 3, but it should be less than 1 by 2. What is that? So basically intersection is basically this region here. This basically is a z equal to 1 by 3 unit circle. So everything outside this unit circle is the ROC of the first term. Okay. And z equal to 1 by 2 is the z equal to 1 by 2 is the second circle, but everything inside is the ROC for the second term. The only intersection is this annular region. Okay, that is the intersection. And that's why we say this is the ROC. And what are the poles and zeros? Go back to the expression for Z transform. For numerator polynomial has only one Z. So the zeros are only, it has 1 0 equal to 0. Poles are denominator polynomial equal to 0. So you'll have the factors are z minus half and z minus 1 by 3. So the denominator goes 0 at z equal to half and z equal to 1 by 3. So plot, so basically it has only 1 0 at 0. And at 1 by 3 and 1 by 2, it has two poles. And the ROC is a annular region between 1 by 3 and 1 by 2. Again, this matches our intuition that it's a two-sided signal, so its ROC should be an annular region. Finally, half power n u of n plus 1 by 3 power n u n minus n minus 1. What I did, I've just swapped. So here I gave u of minus n minus 1 to half power n, but I gave positive u of n for 1 by 3 power n. Now I will give the positive value for 1 by 2 power n, and I'll give the negative u minus 1. That is the u of n being left-sided to 1 by 3 power n. I've just flipped it. So x of n, let's say the first term, has a z transform z over z minus half. So basically, since it's a right-sided signal, the ROC should be such that mod is greater than half. Now, for the second signal, has x2 of n equal to 1 by 3 power n by u of minus n minus 1. The z transform comes out to be minus z over z minus 1 by 3, with the ROC being mod z is less than 1 by 3. This is because it's a left-sided signal, so the ROC is interior part of the circle, mod z equal to 1 by 3. Now, what is the common ROC is the intersection of both of them. So let's say you see mod z greater than half, so that is this, and mod z less than 1 by 3, and that should be interior part of this. So if I want to find the common region, there is no such common region. Why? Because for the first signal, it should be outside half. Second signal should be inside 1 by 3. There is no common region that intersects both the ROC. Therefore, if there is no common ROC, that means there is no region of convergence for this at all. There is no region of convergence, that means that no value of z will the z transform exist. Everywhere it will diverge to infinity. Therefore, basically, this particular x of n will not have z transform. Is it clear? Can anyone unmute and tell if this is clear? Okay, I see on chat that someone has told it's clear. Okay, let's then move on. X of n, the next question is x of n equal to a power mod n, and a is some positive number. Assume it to be real also, no problem. First question is sketch x of n when a is less than 1 and when a is greater than 1. Second question is find the z transform for this x of n and sketch the pole zero plot and ROC when a is less than 1 and a is greater than 1. Okay, so now let's just understand what. So recall that mod n equals value n when n is a positive number, or it's minus n when n is a negative number. Okay, therefore x of n is nothing but a power n when n is a positive number, a power minus n when n is a negative number. Okay, now if a is less than 1, how does a power mod n look like? It will if a is a number less than 1, it will go to 0 as n goes to infinity. Right? So it is basically like if let's say at a is equal to half. So at n equal to 0, it is 1. then it is half, then it is 1 by 4, then it is 1 by 8, which is 1 by 2 cube, right? 1 by 8, then 1 by 16, and so on, it will go to 0. Okay? Depending, so all it says is, maybe the exact amplitude is not, we cannot tell because that depends on the actual value of A. But all we can say is that if A is less than 1, as n goes to infinity for a very large time index, it will go to 0. It will go to 0. Okay? That is the meaning of that's basically the interpretation of the signal, time domain signal, where n is less than 1. But when n is greater than 1, what happens is the amplitude keeps boosting up. For example, if A is equal to 2, at n equal to 0, it is 1. At n equal to 1, it's 2 power n 2. At n equal to 2, it's 2 power 2, 4. At n equal to 3, it's 2 power 3, 8. So it becomes 1, 2, 4, 8, 16, and so on. At n tends to infinity, x of n will also go to infinity. That's why it is actually an increasing function of n. And it's both symmetrical with respect to positive x-axis and negative x-axis. That's because of the function. You see, it is a power mod n. So basically, a power n will be same as, let's say, a power, basically x of 2 will be same as x of minus 2, because both will same map to same mod n. Similarly, x of 10 will be equal to x of minus 10. All will be same because you have a power mod n. It is symmetrical about your y-axis. That's why you, in both cases, a less than 1 and greater than 1, the values are symmetrical. Okay, this is the first question. The second question is, find x of z for this x of n and sketch the pole 0 plot on ROC when a is less than 1, case 1, and case 2, a is greater than 1. So let's, x of n is basically this value. A power mod n takes a value a of n, a power n if n is positive, a power minus n if n is negative. Okay, so you can write, so basically that means what? You can write this x of n compactly as a power n times u of n plus a power minus n times u of minus n minus 1. So that whenever n is negative, the first term is 0. Second term, basically this u of minus n minus 1 equal to 1. So it's just a power minus n. And whenever n is positive, the second term is 0. And in the first term, u of n is equal to 1. So it's just x of n is a power n. So that basically you can write this representation of x of n compactly using a unit step function. Okay. So call the first signal as x1 of n and the second signal as x2 of n. Okay, so recall that a power minus n is same as 1 by a power whole 1 by a whole power n. So a power n u of n has the z transform z over z minus y a, and 1 by a power n u of minus n minus 1 has z transform z over z minus 1 by a, with ROC in the first case being exterior part of the circle mod z equal to a. That's because first signal is a right-sided signal. And for the second signal, it is a left side, it's a left-sided signal. So it will be interior part of the circle mod z equal to 1 by a. That's because now it is a pole occurs at 1 by a. So now basically what happens when a is less than 1? When a is less than 1, basically when you look at mod z is greater than a, right? And a is less than 1. So basically a is somewhere in, let's say, so for first what we will do, we will draw a unit circle. This red color one is a unit circle. I'm marking it here. Okay, now a is less than 1, so mark a z equal to a is inside the unit circle. So if a is less than 1, 1 by a will be greater than 1. So mark the, so the circle with radius 1 by a will come outside the unit circle, that is mod z equal to 1. Okay, so these are the three circles. Now what it says, z is greater than a. That means everything outside these pink color lines are the ROC for the first x1 of n. And for the second signal, mod z should be less than 1 by a, or it should be interior to the outer circle 1 by a. Therefore, what is the common region? From a to 1 by a, that annular region, right? This annulus is the common ROC. And there are two poles, one occurs at a and another is 1 by a. Okay, so common ROC is annular region between a and 1 by a, with poles at a and 1 by a, and 0, it has only 1 0, because if you basically solve for this, we just add both of them, z by z minus a plus z by z minus 1 by a, you can show that that resulting numerator will have only 1 0 at 0, z is equal to 0. Okay, so this is the scenario for z a less than 1. Now what about a greater than 1? Okay, yeah, this is what I'm saying. For the a less than 1, if you add both of them, you will get only one z polynomial in the numerator, of course scaled by some constant, but that is independent of z. So if you equate numerator to 0, only z is equal to 0 as a 0. And poles occur at a and 1 minus a, and the ROC is mod z between a and 1 by a. Now, when a is greater than 1, what happens is that when a is greater than 1, your mod z equal to a, that circle will be outside the unit circle, and 1 by a will be less than 1. So that will be inside the unit circle. And basically, the first equation says that your mod z should be greater than a. The second equation says that mod z should be less than 1 by a. Now go back to this figure. That means I should mod a should be greater than a. That means should be exterior part of the circle, unit the circle with a, and mod z less than 1 by a means interior part of this purple circle. Now what is the intersection? There is no intersection at all. There is no common overlap between these two ROCs. Therefore, if there is no common intersection, therefore the Z transform does not exist when A is greater than 1. Is it clear? Are there any doubts? Can anyone please confirm if it's okay, if everything is clear? Hello, are there any doubts? Can anyone confirm if everything is clear till now? Are you able to understand? Okay, so can you just, okay, there's a comment. Can you just state the answer of part A of previous question? Okay, means you mean question number 5 or question number, this same question, or are you asking for question number 5? Okay, question number 5. Okay, and you are asking for A part. Okay. Okay, this is A part. The question, let me just repeat it again. The question says, find the Z transform of X of Z, that is Z transform X of Z, whole zero plot and ROC. Okay, so you are asking for A part, that is X of n is equal to half power n U of n plus 1 by 3 power n U of n. Okay, that's what I'm writing here. So half power n U of n will have the Z transform Z by Z minus half. 1 by 3 power n U of n will have Z transform Z minus Z by Z minus 1 by 3. The first half power n U of n, the ROC is mod Z greater than half. I mean, how did I get it? Because the pole occurs at 1 by half, sorry, 1 by 2, and it is a U of n, it's a right sided signal, so it should be exterior part of the pole, so mod Z greater than half. Similarly, for the second signal also, it's a right sided signal and pole occurs at 1 by 3, so the ROC is mod Z greater than 1 by 3. Now, the total Laplace Z transform is given by linearity property. It's a Z transform of the first signal and the plus Z transform of second signal. And that's what I'm doing here. I'm just adding both the Z transform, and that if you calculate, so take LCM. So basically, for the first time, multiply by Z minus 1 by 3 on numerator denominator, and for the second term, multiply Z minus half on numerator denominator. You just simplify, you will get this number here. Now, how to find the ROC? ROC is nothing but intersection of both the ROCs, right? So let me just draw here. So what Z greater than half, right? Let me just draw Z greater than half. This is mod Z equal to half. So Z greater than half is this. This is the ROC. Now the second ROC is Z greater than 1 by 3. So let me, so 1 by 3 is less than 1 by 2. So that Z mod Z equal to 1 by 3 will lie inside mod Z equal to half. And exterior part of that's mod Z equal to 1 by 3. So this is the ROC for the second one. Now what is the intersection? Intersection is whatever is lying outside Z equal to half. Because between in the annular region between Z equal to 1 by 3 and 1 by 2, the ROC for Z greater than half will be violated. It will not occur. The common intersection is Z greater than half. Okay, that's what I wrote here. The intersection of the regions given by mod Z greater than half and mod Z greater than 1 by 3 is mod Z greater than half. Is it clear? This is what I told. And pole zero plot basically means what? You take the zeros of the numerator, equate to 0. That comes at Z equal to 5 by 12 and 0. take the denominator polynomial in z equal to 0, and that occurs at poles half and 1 by 3. Just plot them. So 5 by 12, that is basically here on the x-axis, and now 0 is at 0. Poles at 1 by 3 and 1 by 2, that is basically these two. And the ROC is outside mod z equal to half. Okay. Fine. Okay, let's move on. Okay. Next question. Consider a discrete time LTI system with impulse response given as h of n equal to alpha power n u of n. Okay, this is the impulse response of a discrete time LTI system. Question is, examine the conditions under which the system is a causal system and B system is Bibo stable using Z transforms. Okay, so we are just going to use the properties of these two, causality and the stability, like in terms of how should the ROC be or for a Bibo stable and a causal system. Just using those properties only, we're going to solve the question. So for that, what we need to do is we need to find the transfer function. That is, take the Z transform of h of n, impulse response. So h of n is equal to alpha power n u of n has a Z transform, Z by Z minus alpha with mod Z greater than alpha as the ROC. That's because the right-sided signal. So your mod Z greater than alpha is the ROC. Okay, so that means ROC is exterior part of the circle. Now, the system is basically causal for any value of alpha. Why? Because for a causal system, all you need to ensure is that your ROC should be exterior part of some circle. It doesn't matter what is the radius of the circle. It should just be exterior part of some circle. It doesn't matter what is the value of alpha. It should be exterior part of that circle, and that is why exactly what the ROC is also. Therefore, this h of n is causal for any value of alpha. In fact, you can also look at the time domain signal. Time domain impulse response is right-sided, and we know that from the second class itself that a right-sided impulse response is always a stable system. Sorry, a causal system. Okay, right-sided impulse response is always a causal system. Therefore, for under what the question says, and examine the conditions under which it's causal. The answer is that under any condition the system is causal. Now, second is what under the condition of Bibo stable. Okay, now for stability, the requirement is that the unit circle mod z equal to 1 should be a part of region of convergence, should be part of ROC. Now what I know is that ROC is exterior part of circle with radius alpha, mod alpha. Now, if unit circle has to be included in ROC, that means necessarily the circle mod z equal to alpha should lie inside the unit circle, because the ROC is exterior part of the circle mod z equal to alpha, and if that ROC has to contain the unit circle, the alpha value should be less than 1. Only then the exterior part of the circle mod z equal to alpha will contain the unit circle. Okay, therefore, for Bibo stability, mod alpha should be less than or equal to 1. If it is more than 1, then it is not a stable system, because if it is more than 1, then mod z equal to alpha will lie outside the unit circle, and exterior part of mod z equal to alpha will not contain the unit circle. Is it clear? Is it clear?
Yes, sir.
Okay. So basically, for causality, it is for any value of alpha, but for stability, your alpha must be. In fact, it's okay. In fact, I think equality should not be there, because alpha is basically the pole here, right? Pole is given by alpha, and the ROC should not contain pole. So if the unit circle has to be inside ROC, alpha should be strictly less than 1. Equality should not be there. So I'll just erase the equality symbol. Okay, and put equality for non-stable. It's unstable if alpha is greater than or equal to 1. It is stable if it is strictly less than 1. Okay. Now let's move to the next question. The question is as follows. Consider the discrete time causal system. So it's already given causal. Okay, very important. We'll use this property in the answer as shown below. So what it says, that you give an input x of n, and this is some system, some black box. Okay. and the output is y of n. And this is how the black box does these mathematical operations. Okay. Now the question is, you see, this box is characterized by one variable called k by 3. You understand z inverse means it's a delay. Okay, why delay? You go back to the equation, I mean properties of Z transform. If you look at the properties of Z transform, if you delay, let's say n not equal to 1, that means you get Z power minus Z inverse time x of Z. So whenever you multiply your x of Z by Z inverse, that means you're inherently delaying in the time domain by 1 unit. Okay, this is something you need to keep in mind. In digital signal processing courses, you will encounter many block diagrams which will be something of this form: Z inverse. So x of n will be passed through a block whose with which will be denoted by Z inverse, and y of n will be the output. This means y of n is equal to x of n minus 1. This delay unit, it's called a delay unit. When I put Z inverse, that means it delays the input by 1 unit. Okay, that's because of this representation. If n not equal to 1, that means x of n minus 1 will have the Z transform Z power minus 1 into x of Z. Okay, it's just for information. Now let's go back to the question. Okay, so here Z inverse means what? If let's say input is x some q of n, then output will be, sorry, if the input is q of n minus 1, the output will be q of n. Oh, okay, sorry. The input is given from right side, right? See the arrow mark very carefully. That's why q of n is given as the input from right side. So the output will be q of n minus 1. That is the meaning of Z inverse. Okay, the question is, and then what values of k will the system be BBO stable? Where is k coming? K is coming here. So basically it multiplies signals. So here q of n minus 1 is the input. The output to this block will be k by 2 into q of n minus 1. Just multiplies the signal by a constant k by 2. Similarly, here the output of this k by 3 will be k by 3 into q of n minus 1. And that will go with the addition here. Okay. So now basically let's try to write down mathematically what this block is doing. So you see, first equation q of n, write the expression for q of n. What is q of, where is q of n? Q of n is here. And that is obtained as the output of this adder. Correct? Maybe I'll change color. See, this is the adder here. The output of this adder is nothing but q of n. Therefore, what is the input to this summation? X of n plus k by 2 into q of n minus 1. That's what I'm writing here. Now, second equation is for y of n. Y of n, the y of n is obtained as the output of this summation. What are the two input to summation? K by 3 into q of n minus 1 plus q of n. And that is the second equation. Can anyone tell me if at least these two equations are clear? How did I get these from this diagram? If these two are clear, then everything else is just simplification. Is this clear? How did I get these two equations from this diagram? Okay, I see an S in the chat. Let's continue. Okay, so that's all. Now we'll forget about diagram because you have written the diagram mathematically in these two equations. Okay, now what we'll do, we'll take Z transform on both sides to both the equations. The first equation will give Q of Z is equal to X of Z plus K by 2 into Q of n minus 1 is nothing but Z inverse into Q of Z. That's the property we just saw, time shifting property of Z transform. Similarly, for second equation, you have Y of Z equal to Q of Z plus K by 3 into Z inverse of Q by Z. Okay, now what we'll do, we'll rearrange both the equations. What that is basically, in the first equation, you have Q of Z in the right hand side and the left hand side. Bring this Q of Z to left hand side. And then take Q of Z common. You get 1 minus K by 2 Z inverse into Q of Z equal to X of Z. That is equation 1. Similarly, for second equation, take Q of Z common from here. What you will get is 1 plus K by 3 Z inverse into Q of Z equal to Y of Z. That is equation 2. Now what you do, you divide both the equations. If you divide both the equations, that is 2 by 1, not 1 by 2. Okay, take second equation and divide by the first equation. And what you do, Q of Z and Q of Z will get cancelled, and we'll get Y of Z by X of Z, but that is nothing but H of Z, the transfer function of the system, by convolution property. The ratio of the output Z transform to the input Z transform is the transfer function. And then basically Q of Z will cancel. what you're left out is 1 plus k by 3 z inverse over 1 minus k by 2 z inverse. And that is nothing but z plus k by 3 by z minus k by 2. All you need to do is invert the z transform. You need to do inversion, because what is the question? Oh, sorry. I'm sorry. You don't even need to do inversion, because you're not asked to find impulse response. You're only asked to find for what values of k is the system be more stable. That's what you need to find. Means what? For stability, unit circle should be included in the ROC. Now, what is the R? What is the pole? K by 2 is the pole of this, because denominator equal to 0 is nothing but k by 2. If the ROC should include the unit circle, that means k by 2 should necessarily be less than 1. Why? Because the ROC, what is the ROC of the h of z? It is exterior part of the circle. K by 2 greater than, sorry, mod z greater than k by 2. Can anyone tell me why did I not say mod z less than k by 2? Can anyone tell me why can this not be the choice? I only chose the first one as a choice. Yes. Can anyone tell me why is the ROC for this Z transform mod Z greater than K by 2? Yes. Can anyone tell me? Okay, let me give you the hint. That's why this property causal is given. For causal system, the ROC is exterior part of some circle. I know that the circle is mod Z equal to K by 2. Now the question is whether it is outside the circle or inside the circle. The question is given causal. That means the ROC should be outside the circle. That's why the ROC for this is nothing but mod Z is greater than K by 2, not less than K by 2. Okay. Since the system is causal, the ROC is mod Z greater than 1 by 2, K by 2. Now, what is the requirement? The requirement is it should be stable. It's already given it's causal. Okay. Now it should also be stable. That means this k by 2 should be less than 1. Only then the unit circle will be inside the ROC. Just like the previous question, right? In the previous question also we told that mods are greater than alpha is ROC, and only if alpha is less than 1 will my ROC contain unit circle for it to be stable. Same logic here also. My ROC is mods are greater than k by 2, but if it has to be stable, this mod k by 2 should be less than 1 or k should be less than 2. Then the system will be stable. Okay, so the question was for what values of k is system Bibo stable? The answer is mod k should be less than 2. Then the system is Bibo stable. Okay. Next question is find the inverse z transform of this x of z and given ROC is mod z less than 1. The first step what we will do is we'll convert x of z into proper rational fraction. That is the degree of the numerator is less than the denominator. Now here degree of denominator is 2. The degree of numerator is 3. This is an improper fraction. I'll make it proper first. How do I do? You divide numerator and denominator by long division. The numerator is this, denominator is this. So take the first term, 2z cube divided by z square is something but 2z. So then basically multiply 2z by the entire divisor. You will get 2z cube minus 6z square plus 4z. You subtract both. What you get? You get this becomes z square and this becomes minus 3z and bring the plus 3 also down. Okay. Now the new first term is z square divided by z square will be equal to 1. Okay. So then multiply 1 by the divisor, which is z square minus 3z plus 2. Now take the difference. You will get equal to 1. That means the basically what it dividend equal to quotient into divisor plus remainder, right? Basically you use that and then you basically rearrange things. You can show that your x of z, the dividend, is equal to the quotient plus remainder by divisor. You can show that your x of z, this is now nothing but this term here. Okay. Now basically what this 1 by z square minus 3z plus 2 is, you can do nothing but 1 by z minus 1 into z minus 2. Now what I will do is I will just do partial fraction expansion of, Let me just concentrate on the last term, call it x1 of z. I'll do partial fraction expansion of x1 of z by z. This is basically the procedure. You divide by additional z here. Okay, so that means x1 of z is nothing but 1 by z minus 1 into z minus 2. If you divide by z on both sides, you get x1 by z is equal to 1 by z into z minus 1 into z minus 2. Or this has three poles at z is equal to 0, at z equal to 1, and z equal to 2. So you can write this as in partial fraction expansion, c1 by z plus c2 by z minus 1 plus c3 by z minus 2, where c1 is given by basically x1 of z into z at z equal to 0. It is nothing but 1 by z minus 1 into z minus 2 at z equal to 0, which is equal to half. Similarly, you can find c2 is equal to z minus 1 into x of z at z equal to 1, which is, you can show that becomes minus 1. And c3 is equal to z minus 2 into x of z at z equal to 2, which is equal to half. This is exactly same as what we did in while inverting the Laplace transform. Exactly same steps. Okay. And now put it on x1 of z by z is nothing but now this term here. So, or you bring this z, now take this z on the left hand side to the right hand side. So it becomes x1 of z equal to this big term here. Okay. Now this is nothing but x1 of z. But what is x of z? 2z plus 1 plus x1 of z. That is basically, and there's another half from x1 of z. So half plus 1 is 3 by 2 minus z by z minus 1 plus half into z by z minus 2. And in the question, it's already given that ROC is mod z less than 1. Okay. Now all you need to do is you have gotten the final z transform. You need to just invert term by term. You need to invert it to the time domain. Now 2z has the left, basically its inverse is nothing but 2 of delta of n plus 1. Now why did I say n plus 1? It's a left sided signal. It takes a value 1 at n equal to minus 1. That's because, see, the ROC is left side. It's inside the unit circle. It's inside a circle, in fact, right? So it's a the signal must be a left sided signal. That's why while inverting every term, I need to ensure that the time domain signal is a left sided signal. Now for 2z, you can, by property of z transform, you can show that delta of n plus 1 for you will have the z transform z with ROC mod z less than 1. Similarly, 3 by 2 is a constant, so it's just 3 by 2 times delta of n, because delta of n has the z transform 1. Recall that, right? Now z by z minus 1 with ROC being an interior part of circle will have the inverse z transform u of minus n minus 1. And the last term will have half into 2 power n into u of minus n minus 1. Okay, so all of these are left sided. That's because the given ROC is interior part of a circle. Therefore, just collect all the group terms things together, and you will get this big expression for x of n here. Is it clear? Are there any doubts? Please confirm, just so that I can go to the next question.
Clear, sir.
Okay. Okay, now we are going to the last question for today. Again, inverse Z transform question. So basically the question is that we need to invert x of z equal to 2 plus z power minus 2 plus 3z power minus 4 divided by z square plus 4z plus 3, and given ROC is mod z greater than 0. Okay. Now what I will do is I will multiply and divide by z. Okay. So basically the first numerator by z into z by denominator. Okay, I will tell you why I'm doing this separation. Okay, so the first term is as is. Okay, what you do basically you divide by z. So 2 by z is nothing but 2z inverse. Z power minus 2 by z is nothing but z power minus 3. Z power 3 z power minus 4 by z is z power 3 z power minus 5. Similarly, here you have z by z square plus 4z by 3. And that you retain and call this as x1 of z. Now we'll compute the partial fraction expansion of x1 of z. It's x1 of z is nothing but z by z square plus 4z plus 3. But generally we take the partial fraction for x1 of z by z. Okay. So then basically what you do, this z will get knocked off. So it just x1 of z by z is 1 by z square plus 4z plus 3, which is nothing but 1 by z plus 1 into z plus 3. Do partial fraction is nothing but c1 by z plus 1 plus c2 by z plus 3, where c1 is equal to half and c2 is equal to minus half. Fine. Therefore, your x1 of z is nothing but half times z by z plus 1. See, I did this for x1 of z by z. Now take this z back to the RHS. So it becomes x1 of z is equal to z by z plus 1 into half minus z by z plus 3 into minus half. That is c1 by z plus 1 plus c2 by z plus 3, but you multiply z on both sides because you brought the z from the denominator to the right hand side with ROC mod z greater than 0. Now you see, what did I do? Basically, this is still pending, right? 2z inverse plus z power minus 3 plus 3z power minus 5 times x1 of z. I'm just writing it down here. Okay. Therefore, now let's take the inverse z transform. I'm going to use a property of inverse z transform, namely that if x1 of z has the inverse z transform small x1 of n, then 2 z inverse into x1 of z will have the inverse z transform 2 x1 of n minus 1. That is, whatever is the power of z power minus will be the time. This is basically time shifting property of the z transform. Similarly, for the second term, you have z minus 3 times x1 of z. So it becomes x1 of n minus 3. Similarly, for the third term, you have 3 times z power minus 5 into x1 of z. So third term inverse z transform will be 3 times x1 of n minus 5. Okay, so now I've inverted one step. What is that? I've taken care of the first, but I still didn't take care of second. Uh, I need to still find x1. What is the value of x1? So what remains to compute is what is the signal x1 of n. But I know that the Laplace transform of x1 of n is nothing but x1 of z, which is given here. Half into z by z plus 1 minus half into z by z plus 3 for ROC greater than 0. Okay, and that's, you can show that wait, so ROC is greater than 0. That means it's the exterior part of the circle. So here it's a circle with radius 0. It's just origin, but still the exterior part. So that means your ROC, your x of n should be right-sided signal, and you're delaying by 1. I'm sorry, you're taking the e power 1 power n and 3 power n. That's why, sorry, minus 1, because it should be z plus 1, and similarly it's minus 3 here. So it is half of minus 1 power n u of n minus half of minus 3 power n u of n. This is basically my x1 of n. And now I found out x1 of n. Substitute this back in 1 because I am delaying by 1, 3, and 5. So if you substitute it back, you can show that your x of n is given by this big equation here. Okay, so basically here, the why did I solve this is a trick, one small trick you can apply, that you don't always need to see. The problem here is that 2z inverse is getting multiplied, right? So it may be a bit difficult to find out what is the inverse. Basically, it should be like convolute. One way to do is find the inverse z transform for this separately, find the inverse z transform for this separately, and convolve both the sequences, because convolution in the time domain is multiplication in the z domain. That is one way to do. The other way is cleverly noticing that the structure of the first signal is such that each one is delay unit. The first one delays by a unit of 1 and multiply by 2. The second number will delay by a unit of 3 units. The third will delay by a factor of 5 units and multiply by 3. So you just recognize that structure, and then all you need to do is just find the inverse of the second term, and then do time shifting of the second term. That's what is basically this equation 1. And then you just find x1 of n, that is going to be equation 2, and put that back in equation 1. You will get this big chunk, big time domain signal. Is it clear?
Yes, sir.
Okay. Okay, fine. So great. Actually, it's correctly on time at 8. If there are, so my plan was basically to make a trial and see, whether it's good to have a pre-written notes and go over them, or should I write along in the live. So it turns out that if I do a pre-written notes, then I can cover more number of questions. You always will have the notes with you. You can go through them slowly. Or if you would like me, I can do it live, but maybe I might not be able to do more questions. So whatever you guys suggest, I will follow it from the next class. So what do you think? Which is a better approach? Yes. Which one would you prefer? Is this approach fine, or do you want me to solve uh, the answers? But in that case, you might not be able to do more questions. Is this pre-written approach okay? Can I write it before and then flash like this and explain step by step?
Yes, sir. This is okay, sir.
Okay, fine. Then let's do this from the next class. If there are any objections, you can tell me right away. There are no, then I will assume that you're all are okay with this approach. And then I'll do like this and I can cover little more questions from next class.
So can you download these questions in NPTEL?
Yes, yes. I think all these, whatever I'm flashing, right? All these notes will be available as PDF for you. So you can download and then you can save it in locally and then you can print it, do whatever you like.
Okay, sir. Thank you.
Yeah. Are there any questions? Any more questions, comments, doubts?
So after practices, next classes, if any doubt.
Sorry, I didn't hear you.
So after practices this question, next classes, if any question, then
Yeah, sure. You please, there are any doubts you get, feel free to ask me. I can just go over them, go over these again the next class, depending on wherever your doubt is. No problem.
okay. Thank you.
Yeah. Okay. Well, then stop for today. Let's continue again the next class next week. Yeah. Thank you.
Okay. Thank you, sir.
Yeah.